Thank you again for having me, and thank you for the Coppola Award. I'm not sure if this is a CME talk, but if it is, I have no significant disclosures other than my NIH funding. So I wanted to start with acknowledgements because they're the most important part of my research. So I wanted to thank you for the honor of the Coppola Award. It was fantastic and very humbling to get the award. So the nominators were Drs. John Morris and Jessica Mazursky, so I want to thank them in particular. Today, the research I'm going to talk about is for this clinical trial that we are calling We Share, which is Washington University study of having AD research results explained. And so it's a clinical trial to evaluate the impact of returning research results on our longitudinal participants at the night ADRC. And I put the whole study team there, and then I'd also like to acknowledge my long-term primary mentor, Laura Beirut, who I hope will always be my mentor. Let's see. So the issue with disclosing research results is that to date, people have only disclosed one result at a time. So there's been disclosure of the ApoE genotype and exposure and disclosure of the PET amyloid status. So in the REVEAL trial, which was in the late 2000s, I think the paper was published in 07 or 08, the curves so individuals who were at higher risk for Alzheimer's disease, I believe they had to have a family history of Alzheimer's disease, were given their ApoE genotype, and the way it was communicated to them was these lifetime risk curves. The Generations study then updated this and gave the absolute risk of getting AD by age 85. So this was in 2007. And this is a more approved approach in terms of communicating risk, in that it has pictographs to communicate risk, and it gives absolute risk rather than relative risk. So there are these evidence-based recommendations for returning risk. And then in addition, we have to figure out how to interpret the data we want to return. So specifically, individuals want to know what the results mean, understandably. So this is a paper led by my co-investigator or co-principal investigator, Jessica Mazursky, where they studied the A4 trial to understand the impact of returning, to be in the A4 trial, everybody got a PET scan, and the people with positive amyloid PET scans were enrolled into the trial, and the people who did not have positive amyloid PET scans were not enrolled in the trial. So therefore, the disclosure of the PET scans in these cognitively normal people was necessary. So they studied the impact of disclosing this. And so people were given basically a positive or a negative. That is if their PET scan was elevated or not elevated. And in general, people were they wanted more information. They wanted it to be incorporated into risk, and they wanted to know what it meant more to them. So then another layer is that there are multiple biomarkers and genes that we're looking at for Alzheimer's disease, and they keep developing and coming. And so returning a single biomarker, and all of these are obviously related to each other because they're all related to Alzheimer's risk. And so returning a single biomarker or multiple biomarkers in an individual way without compiling them is misleading. So to date, there's no feasible way of returning multiple research results, and we don't know whether the participants understand the combination of the research results. And then in general, the research results should be presented in a way that presents absolute risk, which is based on evidence in terms of communicating risk. So we, for our trial, our plan for communicating the results is first to educate the participants before they consent. So we talk to them about Alzheimer's dementia, about research results, and that they're not clinical results. We give them some pros and cons of receiving their results. We give them, and we give them some example results. And then after they consent, they're given both a baseline risk of AD dementia that's using demographics, and then an adjusted risk of AD dementia that incorporates the biomarkers into their baseline risk. And then they're given a brief summary of the individual results of the biomarkers test, like, positive or negative, that kind of thing. So the way we educate people is we spent quite a bit of time putting together this educational brochure to help the participants decide whether or not they want to receive their research results. So basically the brochure has, an overview of, what's included. And, one of our key points is that these are research results, not clinical results. And we go through pros and cons of wanting to know your research results. And then help participants think about how to apply those to their own life. And then when we give results, what we give is this is the baseline risk. So this is for a participant of African ancestry with their demographic factors. We're giving them a 5-year risk of developing AD dementia. And this person has a 6% absolute risk for the 5 years. And then there's a confidence interval that's between 4 and 10%. And when we give them an adjusted risk, which has the new 5-year risk based on incorporating the biomarkers. So that's in the risk report. So we developed all these beautiful pamphlets and presentations and worked hard to try to figure out what the best way to communicate risk is, but then we also have to figure out how to compute that risk. And so what we're looking for specifically is a model that can give us a baseline absolute risk for Alzheimer's dementia, and then also a biomarker adjusted absolute risk of Alzheimer's dementia. And ideally, we would use an existing model. So there are many models for computing risk of dementia. Not all of them are Alzheimer's, but most of them include Alzheimer's dementia. This is a review from 2019 of all the different models that are available for computing dementia. The ones I highlighted in yellow are late life models. So for adults over age 65, which is the population that we're working with. So even for them, there are, I believe there are like 28 models here. And so we have a lot to choose from. And then since then, several more have been published. The problem is that none of these have what we're looking for. None of them both compute a baseline risk and compute an adjusted risk. using with the absolute risk. So unfortunately, despite the number of models available, none of them would serve our purpose. And so what we decided to do was develop a model that unifies these models in order to kind of maximize flexibility and build on existing data. So our first goal was to start from existing models. So to do that, we started from variables that are in the models of dementia. And then we wanted to maximize model flexibility by first allowing for hierarchical risk calculation, like a baseline and adjusted risk, which is what we want specifically for our trial. But then also we wanted to allow for missing variables so others can use it. So for example, if there's a model that includes a mini-mental status score and somebody wants to use this, but they don't have the mini-mental status score for their participant, they can still use the model. So you don't have to have all the variables that are in the model. The only variable that's required is age, which is the most important risk factor for Alzheimer's dementia. And we also wanted to build a model in a way that it's easy to update. And then our third goal is to maximize the communication. So to build it in a way that uses best practices for communication. And so doing that, we are calculating absolute risk. We're generating this pictograph and we're putting it on a publicly accessible website so that others can use it. So briefly, we, I guess I should call it unified models for AD dementia risk. And I want to stress that this is still in development. We're finishing the manuscript about the models now, and we'll be submitting it soon. But please, so if anybody has any input on the design or things that are unclear, please let me know, and that will also help our research a lot. So we focused on developing 3 different models. One would be a base model, which includes demographics. And then we would have the option for a clinical model, which includes clinically measured variables or psychometric variables, and then biomarker models, and a model that includes biomarkers. The data, so we had multiple different data sets. The primary data set we used for the base model and the clinical model was data from the National Alzheimer's Coordinating Center, which has longitudinal data on the participants nationwide. So our NIGHT ADRC data is incorporated into the NAC data, for example. So we have a data set that we use for training or developing the model. And then we have data sets that we use for validating the models. So the biomarker models were developed using the local NIGHT ADRC data. And they are separated from the clinical model and the base model because the data sets are distinct. So to develop these models, we started with all the variables that were in the systematic review that I showed you earlier, and an updated literature review. So we started with 175 variables, and then we categorized them into which model they would belong to. So either they're clinical or psychometric variables that are variables that would change over time or be measured clinically, demographic variables, which would be static kind of baseline variables that would not change over time, other than age, I guess. And then biomarker variables, which would be kind of require special tests to measure. So this includes genetics and imaging. So for development of the clinical model and the base model, we started with the variables that we identified from the systematic review, and then we filtered by whether or not they were available in the NAC data set. So the base model went down from 12 variables to 6 variables that were available in the NAC data set. And the clinical model included 49 that were also overlapping with the NAC data set. We then filtered again by whether the variable in the NAC data set really is able to be modeled. So we made sure that it doesn't have too many missing values. So we didn't allow for any variables that had more than 25% missing. And we required variables that were somewhat common. So for example, history of traumatic brain injury was a variable that was added to begin with and is in the NAC data set, but there is only, I think, 1% of the people in the NAC data set have had traumatic brain injury, and so therefore it's not a good variable to include in the model. So those are the variables that we excluded at this point. So the demographic variables didn't change, but the clinical variables went down to 29. So then I did something called reverse stepwise modeling in order to make sure that the base model variables were not redundant with one another, and they're all associated with Alzheimer's disease dementia. So using the base model, so this is done with a, it's the statistical approach that I use is a cause-specific Cox model where it's a survival analysis that allows for death as a competing risk. I won't get into details with that, but just for people who are interested. So at the end, we wanted to make sure that all the variables that were in the model were statistically significantly associated with Alzheimer's disease dementia. And so in the end, the base model had 4 demographic variables. And then the base model was used as the foundation for the clinical model, and the 29 variables were added to the base model. And then we did the same reverse stepwise modeling and ended up with 10 additional clinical variables that were in the clinical model. Our approach to the biomarker models was different. Oh, I didn't do that's okay. So the biomarker model, again, we started with the base model and we did reverse stepwise modeling. So we made sure that everything that was in the biomarker model was statistically significant. And so one thing that this did was so ApoE genotype is significantly associated with Alzheimer's disease dementia, but once you incorporate imaging results, MRI hippocampal volume specifically, and the PET amyloid measures, the genotype no longer matters. And so then we decided from there to do 2 different models, 2 different biomarker models, one with the ApoE and one with the imaging data that we were wanting to communicate. So from this modeling, then we extract the hazard ratios or associations with the AD dementia. And we use a methodology called iCares. It's the methodology used in breast cancer to combine to estimate absolute risk of AD dementia that combines data from different sources. So in this case, it would be data from our base model source and the biomarker hazard ratios. And then we ended up with 2 different biomarker models. One is with ApoE plus the base model, and then the other is, so it's MRI hippocampal volume, which is MRI HV, and then the PET amyloid is A beta PET. Results were included with the base model. So just to show you these models, this is the base model. The 4 variables actually, I should probably say that there are 3 variables, because the 4 variables are age, age squared. So what happens is your risk, the strongest, by far, the strongest factor associated with risk of AD dementia is age. So your risk goes up as you age, but the reason why this age squared term is statistically significant is because the increased risk per year kind of tapers off after some time. So like the difference between the risk for people who are the increase in risk from somebody who's age 65 to somebody who relative to somebody who's age 70, is not the same as the increased risk if we're comparing people who are age 85 to people who are 90. So that the risk, kind of the risk difference goes down over time. Women are, after adjusting for these things, women are less likely to develop Alzheimer's and Alzheimer's dementia in a 5-year period than men. And then there's, if you had a parent with a history of Alzheimer's disease dementia, that also increased your risk for Alzheimer's disease dementia. So then the clinical model, you can see there's the base model is here from the previous page. The clinical model includes the base model, which is the first 4 variables here, but then it also includes body mass index, so actually being overweight is protective for a 5-year risk of Alzheimer's disease dementia. Untreated hypertension is, so this is protective for Alzheimer's disease dementia. I think that this is because it increases your risk for death rather than actually decreasing your risk for Alzheimer's disease dementia. And then there's there are psychometric values. So subjective cognitive impairment, so whether or not people believe that their cognition is decreasing, is related to Alzheimer's disease dementia. The functional activity questionnaire that we do, where you ask the collateral source, how well people do bills and taxes and hobbies and that kind of thing. So so an increased score of the functional activity questionnaire means that you have more difficulty with kind of day-to-day activities, and that increases your risk for Alzheimer's disease. The geriatric depression scale is the scale that we use for our MAP evaluations, which is just basically a count of certain types of symptoms of depression. And so depression is known to be associated with the development of Alzheimer's disease dementia. So that's what this represents. And then there's the animal naming psychometric test, logical memory psychometric test, and the mini mental status score. So this is the number of points from 30. So 30 is the max score. So the more you get wrong, the more likely you are to develop Alzheimer's disease dementia. So the model validation, so the way we validate the models is by using 2 things. One is called discrimination and one is called calibration. So discrimination is where we're trying to see how well we separate out red apples from blue apples, for example. So the way we do that is we rank all the apples we have by their estimated risk that we use that we get from the model, and we set a cutoff value. And then based on that cutoff, we see how well we are discriminating green apples from red apples. So if you're above the cutoff, you're much more likely to be a green apple. If you're below the cutoff, you're much more likely to be a red apple. So the quality of kind of how we're able to discriminate these two groups is the discrimination. Calibration, and the way we measure it is with the area under the ROC curve, which some of you may be familiar with. Calibration is more of an average measurement based on the fact that we're looking at absolute risk. And so what we want to do is if we had a bushel of apples where all of those apples were said to have an absolute risk of 20%, we want to know how many of, so we select all apples that have a risk of 20%, we put them in a bushel, and then we look at the bushel to see what proportion of those actually are green versus red. So if you have a bushel where the estimated risk is 20%, then you would hope that the model estimated risk is the same as the estimated risk in the actual bushel. So for calibration, we look at the expected versus observed, which is kind of the comparison of different bushels, and we look at positive and negative predictive values. So in our study, we this is the discrimination. So we have 3 different data sets. The data set that was used to develop the model is this training data, the NAC data set. And then we also tested it on 2 different validation data sets that are distinct, so they're not part of the training data set. And so this is the area under the ROC curve. And what's interesting, so the first model is if you only have age, and if we eliminate the other 2 variables, age is by far gives us the most discrimination. So if we have age only, then the AUC is 76%. If we add the base model variables, it goes up to 77%. And then if we add the clinical variables, it goes up to 79% with this validation data set. And then we also compared it to popular existing models for dementia. So these bottom 5 are all common measures of dementia. So we wanted to see how our models did relative to existing models, given that we developed our model based on these, including these. And so overall, our models did at least as well. And then to estimate calibration, we looked at whether the estimated risk is the same as the observed risk. So this is like this is the comparing of the apple bushels. So here our bushel is age. And so these bushels are subdivided by age. So and this is for the base model, that if we look at the observed proportion is versus so the model estimated proportion is the shaded box where the mean is the line, and then the confidence intervals are represented by the borders of the box. So what we want to see is something like what we're seeing here, where the mean observed value is close to the mean estimated value, and the confidence intervals overlap. And one thing that you can see is that, so this is for 3 different data sets where it's stratified by age, and in all of these situations, we see high overlap between observed and absolute 5-year risk of AD dementia. So we were pleased with this calibration. So that's all I'm going to do with the statistics, but there are a couple of clinically relevant things that I want to point out. So one thing is that this website isn't live yet, but we're developing a website where with this model for people to be able to use, where we would include the demographic risk factors, and all the models can have ApoE in it, and then we can either choose between a biomarker model or a clinical model or neither. So the website will allow people to select the variable that they want, select the value of the variable that they want. All of these variables except for age will allow for an unknown, so you don't have to have it if you don't want to, or if you don't have it. it'll still make the calculation. So then, and it gives, so if you just put the demographics in, it would put a pictogram for just the demographics. If you use the either genetic imaging or clinical models, then it gives you both a baseline risk and an adjusted risk. So our hope is that this can be useful for in many other situations other than for our clinical trial. So the biomarkers, now I'm going to step back and talk a little bit about the biomarkers that we used that we're focusing on for our trial. So we have the PET amyloid scans, we have hippocampal volume from the MRI, and we have ApoE genotype. So the PET amyloid, we have the results are coded as positive or negative, and where a positive scan is associated with AD dementia. And one thing is that the rates of positivity increase with age, and the rates of positivity also increase with the number of E4 alleles that you have. The MRI hippocampal volume is an automated measure of hippocampal volume that's adjusted for your total brain size. And it's thought to be a measure of neuronal degeneration. So decreased hippocampal volume is associated very strongly with AD dementia. In general, hippocampal volume decreases as we age. And as I said, this is conceptualized as a measure of neurodegeneration, whereas the PET amyloid is obviously a measure of amyloid deposition in your brain. And then apolipoprotein E, I'm sure that you're mostly aware of this. There's 3 different alleles for ApoE, E3, E2, E3, E4. E4 has increased risk relative to E3, and E2 has decreased risk. But it turns out that neither E4 nor E2 are important once we adjust for imaging, because they've already made their contribution. So I want to show you the relationship between hippocampal volume, PET amyloid, and AD dementia. So this is a plot where the y-axis is the hippocampal volume, the x-axis is age, and then this is, for this we created bounds that are age-adjusted groups, so that they represent, so if you're age 70 with a hippocampal volume of 9, then you're in the upper third of hippocampal volumes. If you're age 80 with hippocampal volume of 7, then you're in the middle third, et cetera, et cetera. So this plot is kind of designating 3 different groups for hippocampal volume. And so here, this is the actual data that we have. So red means that the PET amyloid scan is positive. Black means the PET amyloid scan is negative. An X means that they were deceased without developing AD dementia first, in terms of a 5-year risk. And then an open circle is that they're alive without AD dementia at 5 years. And then these darker circles are the ones that developed AD dementia. So what I want you to notice is that basically that there are only 2 people in either the upper third or the middle third that developed of hippocampal volume that developed AD dementia. So the risk, if your hippocampus is adequately large, even after adjusting for age, the risk of AD dementia is in 5 years is very low, which makes sense given that it's a marker for neurodegeneration. But this just shows kind of how strongly it predicts AD dementia. So even people who have positive amyloid scans, which are the red dots and X's, that is not nearly as strongly associated with the development of AD dementia than than the hippocampal volume is in terms of 5-year risk. And so here we have 3 different imaging groups. So if we take these and make them into 3 different imaging groups based on hippocampal volume and PET amyloid status. So either we have them, they're in the, so the lowest risk is the people up here who are PET A beta negative. And then we have people in the middle who are PET A beta positive, or people in the lower quadrant that are PET A beta negative. So those 2 are put together. And then the highest risk is the people in the lower quadrant or the lower third who also have increased amyloid. And again, the ApoE doesn't matter at this point. So what you see is this is this shows the more specifically for these individuals, the rates of developing AD dementia over time. So so the x-axis here is time 0, or is time from when they had the PET scan. The y-axis is the proportion of people who developed AD dementia at a particular time. And then the different colors refer to those 3 groups that I just showed you. So again, there's one of these groups basically has a 0 risk. The group where they have the large hippocampal volume, and oh wait, so sorry, I don't think I said the groups right. So so blue is hippocampal volume is increased, or their PET amyloid is negative. Hippocampal volume, and then the second group is the hippocampal volume is in the middle, and PET amyloid is positive, or the hippocampal volume is in the middle and PET amyloid is, or the hippocampal volume is decreased and PET amyloid is negative. And then the third group is that both are positive. So if you're in that first group, you essentially have a 0 risk of Alzheimer's disease dementia within 5 years, which I think is very interesting clinically. So that's the end of my presentation of this paper and what we're doing with our clinical trial. And again, I want to acknowledge all my collaborators and supporters. And thanks again for the award. It's a real honor to be able to present and to receive the award.
Thank you, Dr. Hartz. We have some time now for question and answer. I don't think there's any questions that have been formally submitted. So you can either right now, if there's about 40 of us online, if you would like to come off and ask a question, I think we could handle that, or put it into the chat. But I would like to, while we are queuing up some questions or getting people ready to answer, I'll ask a question if I may. Sarah, what are your plans for how is this going when your clinic, you have some sort of clinical trial about sharing and not sharing results with participants? What's that part of the work and how's that going, or the timeline for that?
So we are doing it by Zoom. We just started. So we're recruiting participants who have had a scan within the last 2 years and just had their annual assessment. And then we're offering them their results. If they want their results, then they're randomized to either receiving the results right now and through Zoom, either now, or the comparison group is receiving the results a year from now.
Mm-hmm.
So so the whole study was, I mean, some of the delay that we've had in terms of starting recruitment was that we we designed the study so that it could be either remote or in person.
Mhm. From your clinical experience doing this for a while now, what are you thinking that you're going to find in the sharing of these results?
I mean, so hopefully it's a negative study in that there's no long-term consequence of receiving your results in terms of research. So the outcomes we're looking at are participation in the study, psychometric test scores, and psychological impacts.
What are the psychological impacts that you're assessing?
So there's the geriatric depression scale, and then there's a scale called the impact of event scale, which is what they used for the REVEAL trial. Those are the primary psychological impacts.
Here's a question that came in. What is the impact on probability of AD if one parent versus both parents have the disease or die from AD, it says?
You know, I haven't looked at that specifically. I mean, I'm sure that it's worse. I don't know whether it's statistically worse or not.
Okay, so that's unknown. We have someone asking if it's possible to be signed up to be part of your research.
So anybody who is part of the Memory and Aging Project will be contacted. So all participants in the Memory and Aging Project will be contacted for participation in this study. The requirements are that you had to have had the imaging scans within the last 2 years. And I believe they're going to start doing the scans again in April or May, that they have a protocol now that they've developed to have safe in-person scans.
So these folks will be automatically the folks that are already enrolled in trials at the center will be.
Well, not try. So this is so it's not the part of the clinical trials. It's part of the Memory and Aging Project or Adult Children Study. Those are the ones. So if the people are cognitively normal and I think age 65 or older, and then you've had the scans, those are the only requirements.
Thanks. Let's see, Dr. Burge would like to know, how does the clinical model compare with the biomarker model?
Oh, I didn't put that up. Yeah, so the biomarker model is, the AUC for the biomarker model is about 86%. And so the biomarker model is better than the clinical model. So the clinical model, I believe, was like 79%.
Okay.